This is Dr. Delahousie. I'm making this video for my summer MAE 3013 class at Oklahoma State University. We're talking about Chapter 7 in the Engineering Analysis course, and there was a question about the Markov process. Now, the Markov process is just one example of the use of matrices, and it's a little different than most engineers are used to, so that's why we introduce it. It's maybe not even really super fundamental to the course, but it's interesting. And the Markov process is a way of computing changes in the world as time goes by. And a Markov process always ends up with a matrix that is multiplied by a vector. So now let's figure out what goes into the matrix and what goes into the vector. The vector represents the state of the world right now. So the world right now is 25, 20, 55. What does that mean for this problem? We're talking about a county that has a certain amount of land, okay, so many square miles, but let's just talk about percentages of land. They have 100% of their land, and they use their land for three things: commercial purposes, industrial or manufacturing kind of purposes probably, and residential purposes. So the state of their land use today, which in this problem is 2004, today 25% of their land is commercial, 20% of their land is industrial, and 55% of their land is residential. This is the state of the world right now, vector. But their land use may change over time. Stuff that's commercial might become industrial. Stuff that's commercial might become residential. Vice versa. Residential land might become commercial or industrial. What are the probabilities of those changes from one kind of land use to another kind of land use? Those probabilities go into the matrix. If you move up on this document that I'm pointing to, this is in the textbook, if you move up a little bit, you're told that if land today is commercial, these three numbers describe what might happen to it. This is the commercial going to commercial number, 70% probability. If it's today commercial, there's a 20% probability it'll go industrial next time. And if today it's commercial, there's a 10% probability that it's going to become residential. Notice these probabilities, which in the problem statement words would have said 70%, 20%, 10%. Those percentages have been turned into fractions. This column tells what happens to commercial. This is the commercial column. The row tells where it's going. This is the commercial column, commercial row. Commercial stays commercial. This is the commercial column to industrial, commercial going industrial. This is the commercial column to the residential row, commercial becomes residential. Okay, the next column is the industrial column because the second row is the industrial row. Got a 10%, if I am today industrial, I got a 10% chance of going commercial. If today I'm industrial, I've got a 90% chance of staying industrial, and I've got no chance of going residential. Notice these probabilities add up to 1. If today I'm industrial, there's a 100% chance something's going to happen. Notice these probabilities add to 1. If today I'm commercial, 100% chance something's going to happen. This is the today I'm residential column. Today I'm residential, there's no way I'm going commercial. Today I'm residential, there's a small chance, 20%, that I'm going to go industrial. Today I'm residential, there's an 80% chance I'm going to stay residential. This column adds up to 100%. Alright, so this column tells what happens to commercial. This column tells what happens to industrial. This column tells what happens to residential. Alright, so if I take the matrix of probabilities, multiply by the state of land use in 2004, do the matrix multiplication, I get these numbers. What do these numbers mean? That in 2009, when that used to be the future, I'm probably going to have less commercial space, 25 to less than 20. I'm probably going to have more industrial space, and I'm probably going to have less residential space. Looks like this is a county that's destined to go industrial. So this is telling me, here's the state in 2004, multiply by the change matrix, get the state in 2009. What if I want to know the answer 5 years beyond that in 2014? Then this 2009 state matrix moves into this spot. I multiply again and get an answer, and that answer will be the state of land use another 5 years out. If I want to go another 5 years out beyond that, I'll take this matrix, put it into this spot, do the multiply, and get another answer, and I'll know how land use is 15, 20, 25 years out just by doing these matrix multiplies. Now let's look at the homework problem that was given. Okay, here's the solution to the homework problem that's been posted. So let me remind you of the numbers. Basically, I'm a manufacturer, and I either am having trouble in my manufacturing process or I'm not having any trouble in my manufacturing process. That's the state of the world. Either I have trouble or I don't. And as a matter of fact, today I have no trouble at all. So I am 100% now, and this is my state of the world vector. This doesn't have to be percentages, but I am a no trouble of state 1. I have no trouble at all, and I have 0% trouble. I've got 100% not trouble. But how are things likely to change? Because in a manufacturing environment, things head from good to bad. Okay, if this is my no trouble column, and this is my I'm starting in trouble column. If I'm starting with no trouble, I have an 80% chance of staying with no trouble. If things are good, I'm probably going to stay good, but not totally. I got a 20% chance of going from no trouble to trouble. I said 20% chance. Okay, if I have no trouble today, there's a 100% probability something's going to happen. Okay, so these two probabilities add to 100%. So if I start with no trouble, likely to stay there, but I might not. Now, what if today I'm already in trouble? Then these numbers tell me what's likely to happen if I am in trouble. If I am in trouble, these two numbers show up as 0.5 and 0.5, which makes it a little bit harder to describe which is which. But this is the no trouble column, but the first row is the no trouble row. The row tells me where I'm headed. If I am in trouble, I've got a 50% chance of heading to no trouble, because it's the no trouble row. But if I am in trouble, I've got a 50% chance of staying there. Notice the diagonal is the stay in there terms. If I'm in no trouble, 80% chance of staying there. If I'm in trouble, 50% chance of staying there. These two probabilities add to 1. Here's my current state today, no trouble at all. Multiply by the transition matrix to tell me what's happening tomorrow, because this is a set of one-day probabilities. Tomorrow I got an 80% chance of being in trouble and 20% chance of no trouble. But what about the next day? Take this number, move it to here, multiply again. 2 days out, I got a 75% chance of having trouble, 20% chance of having none. 3 days out, take these numbers, move them to here, multiply. I've got a just barely 70% chance of no trouble. I got a 30% chance of trouble. Now, this may sound like this plant is just going to be falling apart. This transition assumes that I don't do anything. Okay, if in day 2, if at the end of day 1 I've got some trouble and I fix it, I really go back to this perfect state and start over. So we're not going to run a plant without ever fixing things. This assumes no fixing. But this also describes the Markov process. A matrix of probabilities of how I might change multiplied by my current state of the current situation tells me where the probabilities of where I'll be in the future.